Good morning. In this video, we will be looking into preemptive round-robin CPU scheduling algorithm. Basically, what is round-robin CPU scheduling is, let's assume there is a list of processors waiting in the ready queue. The CPU scheduler picks a process, the first come first served basis. It picks the first process and assign it to the CPU. And that process will be assigned to CPU for a time period. Let's say we call it time slice or time quantum. Let's say 2 milliseconds. So after the 2 millisecond, the process the process under execution is removed from the CPU and moved to the ready queue. And the next waiting process will be assigned to the CPU. Okay, so in this way, the set of processors will be executed in a circular queue manner, or you can call it in a round robin method. Okay, you might have studied the multi-programming. In multi-programming, let's assume you are working in a computer and you open up many applications. Like you are working on a PowerPoint and at the same time you are working on email application, or you are doing a database, you are opening a database application, something like that. So this time sharing method, we call it round robin technique, was used by the CPU. Like time slice amount, the set of amount of time is assigned to each process. Maybe 2 milliseconds for the database, the next 2 millisecond for the PowerPoint, the next 2 millisecond for your email application. Can you get the idea? So in this way it circles between these three processes. So something like that, it's round robin. Okay then. So that's preemptive. Preemptive means it's an opposite of non-preemptive. Non-preemptive means it's the process assigned to the CPU holds the CPU until its execution complete, until it terminates the execution, or it moves to the waiting state. Here in preemptive, it's not like that. While a process is in execution, it will be removed from the CPU and a new process will be assigned to the CPU. We call it context switch. Okay. So that's because every 2 milliseconds or 3 milliseconds we are removing the process which is currently in execution and we are assigning a new process to the CPU. So context switch occurs every 2 millisecond or every 3 millisecond in the time slice. Okay. So that's the idea of round robin, preemptive round robin. So in the question, you have a list of process P1, P2 and until P5, and this is the arrival time and this is the corresponding burst time. Okay, let's look into the arrival time. Sometimes you won't see the list of process where the arrival time is mentioned in the ascending order. No, you won't have that kind of problems also. Here, the arrival times are not in ascending order. See, P1 comes at time 0, P2 comes in time 5, P3 time 1. So it's not in ascending order. So this type of problems also you will receive. So now first we are going to draw the Gantt chart illustrating the execution of the process. When you are trying to draw Gantt chart using the round robin scheduling algorithm, I prefer to draw a ready queue and then the Gantt chart. Okay, because every time when the time quantum finishes, you remove the process from the CPU, move to the ready queue, and you take a ready process from the ready queue to the CPU. So you need to draw the ready queue for clear understanding. Okay. At time 0, actually I tried to draw few. Okay, at time 0, this is the one and only process available in the ready queue. So in the ready queue, I have a process P1. This is the one and only process, comes at time 0. The all other process comes at other time, later time. Okay. So of course you will be assigning P1 to the processor. So P1 takes 3 quantum. Because the time quantum is 3 milliseconds. So for 3 milliseconds, P1 will be in execution. Fine. After 3 milliseconds, it will be moved to the ready queue and the ready process will come to the CPU. Okay then. Wait a minute. Before moving to the ready queue, while P1 was in execution, like at time 1 and 2, in between, at time 3, in between any process comes to the ready queue? Let's check. At time 1, P3 comes. Okay, P1 is assigned, so strike out. So at time 1, P3 comes. Time 2, nobody. Time 3, nobody comes. Okay. So now at time 3, you need to assign the ready process to the CPU and move the process back to the ready queue. So it goes back to the ready queue. Okay then, fine. So P3 will be in execution for 3 milliseconds. So 3 to 3, 3 plus 3 is 6. So P3 will be executed for 6 milliseconds. Okay, before P3, P1 was executed for 3 milliseconds. P1, so remaining is 5 milliseconds. Just I forgot that. Okay then. Now P3 was executed for 3 milliseconds. So pending is I still have 4 milliseconds pending. Fine. Doesn't matter. While P3 was under execution, is there any new process comes to the ready queue at time 4, time 5, time 6? At time 4 nobody came. At time 5 P2 came. At time 6 P4 came. Okay, just note down all those things. Okay, now you will be assigning the new ready process first come first serve. Who is first? P1. So this process is assigned to the CPU and the pending process P3 is moved to the ready queue. So P3 goes to the ready queue again. So now P1 is given 3 milliseconds. So 6 plus 3, 9 milliseconds. So P1 finish 3 milliseconds. So remaining is 2 milliseconds. Fine. Let's check. While it was in execution, is there anybody came to the ready queue at time 7, at time 8, time 9, 7, time 7. No one came. Time 8, P5 came. At time 9, nobody, because at time 8, everyone finished, no new process after time 8. That's good. So now P1 finished 3 milliseconds. So move the P1 back to the ready queue. Okay. Now at time 9, you need to assign a ready process, which is P2. This is the first to come first. Who is ready first? Assign it to the CPU. So P2 comes. Let's look into P2. It needs only 2 milliseconds. Time quantum is 3 milliseconds, but P2 needs only 2 milliseconds. So 9 plus 2, 11 milliseconds. P2 finish its execution. Done with execution. Now, at time 11, I have to assign a new process. Who is coming? P4 will come. So assign P4. And P4, where is it? P4 needs only 3 milliseconds. Time quantum also 3 milliseconds. So 11 plus 3, 14. At time 14, P4 finished its execution. Fine. At time 14, you need to assign a next new process, which is P3. So P3 comes here. P3, okay, needs 4, but anyway, time quantum is 3 milliseconds. So 14 plus 3, 17. So P3 still 1 more millisecond. Okay, fine. So P3 move back to the ready queue. Okay, now who is ready now? P5 is ready now. So let's bring the P5. So P5, the time quantum is, it needs 5 or doesn't matter. 17 plus 3, 20 milliseconds. Okay, so P5 still need 2 milliseconds. Fine. P5 need 2 more milliseconds. Fine. Now at time 20, who is ready now? First to come, first to serve. So first to come is P1. So assign it to the CPU. P1. Okay. P1 needs only 2 milliseconds. So 22, it finished its execution. P1 finished its execution. That's good. Now who is ready? P3 is ready now. So let's bring it back. Remove from the ready queue, assign it to the CPU. So P3 comes to the CPU. It's assigned to the CPU. P3 needs just 1 millisecond. So at time 23, P3 finished its execution. P3 also over. Now who is pending in the ready queue? P5. Remove from the ready queue, assign it to the CPU. So P5 comes here. How many minutes you need? 2 milliseconds. So 23 to it will be 25. So at time 25, everyone finishes. So nobody is waiting in the ready queue. All are finished. All the executions were finished. Just a second. Let me draw. Okay, this is the CPU execution of the processors in CPU, and it's represented in the Gantt chart. Okay. So as like before, let's try to do the average waiting time and average turnaround time. You know the formula, average turnaround time. Let's do for the P1, turnaround time of P1. Completion time. When P1 finished its execution, see, you need to trace from the backwards. In the CPU, in the Gantt chart of the CPU execution, the one you draw, you just start from the right hand side, your right hand side to your left hand side. Okay, backward, from the backward. So try to look for P1 from the backward. Here it is. At what time it finished? 22. So completion time is 22. Arrival time. P1 arrives at time 0. So it's 22. Now P1 finished already. P2. Let's go to P2. P2, it's here. The completion time is 11 and the arrival time is 5. So it's equal to 6. Turnaround time of P3. P3, it's here, 23. At what time it come? 1. So 22. So let's do for P4. P4, look for P4. It finished its execution at 14 millisecond. And P4, it came at 6. So 8 millisecond. So these are all the turnaround time. Okay. Now let's do for P5. The last process. P5 finished at 25th time and then it came at 8. So 17. Okay then. So these are the turnaround time. Now let's try to do the average turnaround time. You sum them all, 22 plus 6 plus 22 again, plus 8 plus 17, divided by how many processes we have? 5 processes we have. So, when you sum and divide, you will get 15 millisecond. Okay, now let's move on to the waiting time. So, let's do the waiting time for process P1. Just now you calculated the turnaround time and you have the burst time. Okay, the original burst time. So the turnaround time here is 22. The original burst time, don't look into the one you strike and write. No, the original, 8. So that is equal to 14. For P2, 6 minus the burst time is 2, 4. Waiting time for P3 is 22 minus 7, 15. For P4, 8 here and then 3 here, 5. And then P5, you have 17 here, 5 here, and the answer is 12. Okay, so now let's try to do the average. So average, this is average waiting time. As like before, you need to sum all of the waiting time for all the processors. And how many processes you have? 5 processes you have. So when you divide, you will get 10 millisecond. So that's it about the preemptive round robin CPU scheduling algorithm. Thank you.